Welcome to this lecture on the fundamental theorem of algebra. Today, we are going to explore one of the most beautiful and powerful guarantees in all of mathematics. This is a rule that ensures no equation is ever left unsolved. Whether you are completely new to advanced algebra or looking to deepen your understanding, we will build this concept from the ground up together. To start, think of solving a math equation like following a treasure map. If you only know how to walk on a single straight line representing the regular real numbers, you might never find the treasure because you cannot move sideways. But if you are allowed to walk anywhere on the flat ground representing the complex plane, you are guaranteed to reach your destination. In algebra, finding this treasure means finding a root, a specific value that makes an equation equal to zero. Now that we understand the landscape, we need to define what we are searching for. A polynomial is simply a mathematical expression made of a variable raised to positive whole number powers. We also use complex numbers, which include an imaginary part based on the square root of -1. The fundamental theorem of algebra states that every non-constant polynomial equation with complex coefficients has at least one complex root. Finding this first root is like knocking over the first domino, leading to a complete solution. This brings us to the mathematical representation of our polynomial. In this standard formula, p of x represents the polynomial function we are trying to solve. The symbol n represents the degree, which is the highest power of the variable x in the entire expression. The terms a sub n through a sub 0 are the coefficients, which are the fixed numbers attached to each x. The theorem mathematically guarantees that there is at least one complex number c such that p of c equals 0. Even if the degree increases and the equation becomes more complicated, this fundamental guarantee of finding a root never changes. Because the theorem guarantees at least one root, we can repeatedly divide the polynomial to break it down. This formula shows that a polynomial is really just a multiplication of its roots, broken into exactly n simple pieces called linear factors. The values c1 through cn represent all the individual roots of the equation. If the degree n increases, the number of roots increases to match it exactly. This means a degree 5 polynomial will always break down into exactly 5 roots. This factorization is a direct and powerful consequence of the theorem we just established. Before we move on, let us see this with a concrete example. Let us find all the roots of the equation x squared plus 4 equals 0. Because the highest power is 2, the theorem guarantees we will find exactly 2 roots. Our goal is to find the values of x that make this statement true. We start by isolating the variable on one side of the equal sign, which we achieve by subtracting the constant term from both sides. This sets us up for the next crucial step. Continuing from our previous step, we now have x squared equal to a negative number. In the complex number system, we are allowed to take the square root of negative numbers. We apply the square root to isolate x, and the plus or minus symbol is absolutely crucial here to capture both possibilities. The square root of -4 gives us our imaginary roots. Combining these, our two roots are 2i and -2i. The theorem worked perfectly, giving us exactly 2 roots for a polynomial of degree 2. Physically, this means the parabola never crosses the real axis. Now, let us tackle a slightly more complex problem. We want to find all roots of the polynomial x cubed minus 1 equals 0. The degree is 3, so we must find exactly 3 roots. We begin by breaking the cubic equation into smaller, more manageable pieces using a well-known algebraic rule called the difference of cubes. This splits our degree 3 polynomial into a linear part and a quadratic part. For the whole expression to equal 0, either the first part or the second part must be 0. This logical split is the key to solving higher degree equations. Moving forward with our factored equation, we set the first simpler part to 0. Solving this gives us our first root, x equals 1, which is a standard real number. We have successfully found one root, but the theorem tells us we need 3 in total. Therefore, we must move on to solve the remaining quadratic part to find the other 2 hidden roots. This step-by-step breakdown shows how finding one root allows us to reduce the complexity of the problem and hunt for the remaining solutions. To find the remaining roots, we take the second part of our equation and set it to 0. We use the standard quadratic formula. In this specific quadratic expression, the coefficients for the squared term, the linear term, and the constant are all exactly 1. We carefully plug these values into the formula. This will reveal the hidden complex roots that we are looking for. It is important to substitute these values meticulously to avoid any sign errors before we simplify the expression in the final step. Finally, we simplify the numbers underneath the square root symbol. This arithmetic leaves us with a negative value, specifically -3, which tells us immediately that the remaining 2 roots will be complex numbers. We separate the fraction into its real and imaginary components for clarity. We now have a complete set of 3 roots, 1 real root and 2 complex roots. A degree 3 equation has yielded exactly 3 roots just as promised. This confirms that our mathematical tools align perfectly with the theoretical guarantee. Now that we have used this formula, let us understand where it comes from visually. While a perfectly rigorous proof requires advanced calculus, we can understand why this works by drawing a huge circle in the complex plane and feeding all those points into our polynomial function. Because the highest power, x to the n, is so much stronger than the rest of the equation, the output forms a giant loop that winds around the center point, exactly n times. This chunk of the proof establishes the starting behavior of our function at very large values, setting the stage for what happens as we shrink the circle. Let us look at this process in action. On the left, you see the input circle in the complex plane, labeled C sub r, which we are shrinking towards the origin. On the right, you see the red output curve of the polynomial. Notice how the output curve winds around the origin multiple times, corresponding to the degree of the polynomial. As the input circle shrinks, the output loops also shrink, pulling tighter and tighter around the center. This diagram beautifully illustrates the continuous transformation of our complex inputs. Continuing our visual proof, imagine what happens as we shrink our starting circle down to a single dot at 0. The output loop must also shrink down to a single dot. Since the loop starts by wrapping around the center and ends up as a dot, the curve must physically cross the exact center at some moment during the shrinking process. That exact crossing point is where the polynomial equals 0. This gives the final result. A root must exist. The intuition here is that a continuous loop cannot vanish without passing through the origin, proving the theorem elegantly. So, we have proven that this theorem holds. This brings us to why it matters in the real world. Without this theorem, mathematics would be full of dead ends where equations just stop having answers. In real life, this theorem is the backbone of engineering and physics. For example, in electrical engineering, circuits are modeled using polynomials. The roots of these polynomials tell engineers if a circuit will be stable or if it will overheat and explode. Knowing exactly how many roots exist ensures airplanes fly smoothly and cell phone signals remain clear. Let us wrap up what we have learned today. The fundamental theorem of algebra guarantees that every polynomial equation has at least one complex root. By repeatedly applying this fact, we find that an equation's highest power dictates exactly how many roots it has. This beautiful rule ensures that our mathematical number system is complete, leaving no equation unsolved. You have now mastered the foundation of complex algebra.